exporting most of our content, and you get to, and some of us in this call were part of our median edition of the um, public Discord community sessions. And this session is being divided across four main stack. And one of the stack which we've started with is frontier session. And basically the frontier session is where we tend to connect different disciplines together rather than holding on to a particular vertical in the deep tech space, because the deep tech is very broad and you have AI, blockchain, electronics, hardware, embedded systems, firmware development, augmented reality, mixed reality, virtual reality. And we are trying as much as possible to see how we can enable cross-pollination of this platform rather than just holding on to one verticals. And if you've noticed that in the trend of content we churn out, the topics of our frontier sessions, and it's tends to cut across some of those verticals. Actually, not all, but you're going to see some point of intersections in our sessions. And we also have the tear down night. So the tear down night is where we come to pick up a product and see how we can dissect that product and know exactly what tech is behind that product, because it's knowing what already exists, and that's how you can build upon that, because sometimes it's difficult to wanting to just imagine from scratch. It's quite difficult. And if you follow most of the backstories behind how China is catching up with the technology of the Western world, and you get to see a lot of these teardowns being done by the research labs and activities in far Asia. So we tend to pick be it a software, complex software products or hardware products, and see what are the technology stacks that are being coupled together to achieve this, or what are the several hardware components, and most importantly, why those components are used, and what are the trade-offs. And yeah, so that's basically the tier down. And so we tend to bring experts, people who are experts in this domain, to look into or present this. So it can be a live teardown of a product, or a teardown that has already been documented and being shared. And we also have the founders. So the third stack is the founders deep dive. So this is where you get to hear the unfiltered stories behind how founders were able to overcome different challenges building a product, be from regulatory to technical challenges. You get to see how founders overcome these blocks and get the product out. So basically, it's unfiltered stories. And most importantly, we're not leaving research paper review from this session, because we need to keep up with every week new papers, new research breakthroughs are coming out. And for you to be able to keep up with the trend, you need to know what breakthroughs has happened, or what theory is no, it's been deprecated, on what the approach people are taking towards solving or addressing key industry issues. So that's the research review sessions, which comes up as part of our community engagement. So today's session, we're going to be looking at building flight controllers from scratch, and we have no other person but Jesutofunmi. I've been following Jesutofunmi for the past 3 years on LinkedIn, and I've been seeing quite amazing product he has been up to. And yeah, building a flight controller from scratch is something you won't expect people to do in this part of the world. It's something, oh, I'm building a drone as a product. Let me buy the ESC, let me buy the chassis, let me buy the flight controllers from different vendor and assemble. But I mean, this is why the community is why we have the Africa Deep Tech community, to democratize the access to the fundamentals. We are trying to see how we can de-risk people to go down to first principles and build up from there. So without saying much, I will hand over the mic to Jesutofunmi to hit the ground running. And yeah, so it's a community. Hi, sorry, Jesutofunmi, I don't know if you heard me. I, I think I
All
passed the
right.
mic on to you.
All right. Sorry. I think I had issue with internet connection. All right. So, hello everyone.
Okay.
My name is Jesutofunmi Kupoluyi. I am an embedded systems engineer, and I'm also the founder and CEO of JIMS Innovations. So, in this session today, I'll be talking about building flight controller from scratch. So, let's dive into it. So for a lot of us, we know that building a drone is made up of flight controller, motors, frame, electronic speed controllers, maybe even GPS. Now, it's very, very known that most builders don't actually build flight controllers from scratch. So they actually buy it off the market. They flash a popular autopilot stack, like let me say Autopilot or PX4. They configure a few parameters and they fly it. That's the general way that people do things. But for a builder that wants to actually build a unique product, you actually find out that you run into a wall. You figure out that you are not actually in full control of the system because now you are dependent on a product that was developed with a different hardware assumption from what exactly you want. Like, let me say, their choice of components, their choice of microcontroller, or things like that. You are depending on a product that is actually has a different software architecture, a product that has a different priority, and a product that actually has a different limitation from what you have. Then you actually stuck with building from scratch, having to develop your own core stack. Now, let's move from here and let's explain, why do you even bother building from scratch? Why bother at all? Why can't you just find a different vendor, a different product, or let me say, find support from a different person? Why don't you just give it to someone else to do it for you? Now, we actually build from scratch because we want control, because we want flexibility, or maybe because existing solutions don't fit. Now, I'll give an example, which is what I'll share. When I was coming up building embedded systems, I used to ship this popular Arduino Uno board. I'll package inside an enclosure. I will ship it off to my client. But as I moved on forward, I began to realize that rather than me using this entire development board, I can actually use the Atmega 3280P, the chip right on that board. I could use that alone and I will still deliver my product. Now, as I progressed in technical capabilities, I was able to do that. I could use the chip with a simple voltage regulator, attaching an external crystal, and package that together and ship off with the product to my client. And I had better margins. I had full control of the system. I could do more than I would have done when I was just shipping the entire development board with it. Now, this particular activity of building from scratch gives me the flexibility I want in innovation. I can do it in a different way than I would have normally done it. I could put it in a smaller layout than what I would normally do. So that same principle applies here too. Now, I'll also give you my personal experience too. Let's go to the next slide and see that. I want to show you what real ownership looks like. So there was a particular time I actually worked on repairing a DJI Phantom 4 drone for a state security agency. So I was to repair this drone. There was a gimbal part of that drone where the gimbal is the part that stabilizes the camera. I also fixed that particular part. So I had to open the entire thing, tear it down, and figure out what was going wrong. But when I was looking into the internals of this thing, it was very, very mesmerizing because DJI had made they had made custom chips. Their design, their layout was very, very nice. I found out that they are not like a lot of builders like me and a lot of other people that will buy flight controllers from a vendor and take ESC, that's electronic speed controller, from another vendor and bring that all together and make a product. They actually owned the motor, was designed by them, the propellers, the frame, the camera itself, the gimbal circuitry, the flight control circuitry, the electronic speed controller circuitry, everything all developed by themselves. They were not just assembling components. They had tightly integrated systems, and everything was designed to work together. They own the entire thing. That is why today now they are the one with the largest share of the drone market, the commercial drone market, and nobody can actually match their performance. So, in summary, if you don't actually own the stack, you don't actually control the system. For a lot of us, we built the drone, we buy the flight controller, we flash an autopilot stack, and we fly the thing. Wow, we built a drone from scratch. But there are actually levels to this particular activity. For some people, they build the hardware from scratch. They made the PCB design, but they flashed it with a common autopilot stack like Autopilot or PX4. Some people, another level, they build the flight controller from scratch, and they also, let me say, they take an open source flight controller stack, they modify that and combine it together, and they say they build a drone from scratch. That is another level. But now the level I'm talking about is when you actually build the flight controller hardware from scratch, and you also build the flight stack, the firmware also from scratch. Now let's move on. Now I'll show you what I've actually done. So before I play the video, let me pause that a bit. 1 second. So this is what I've done. I've actually built the flight controller hardware from scratch, done the firmware, and also done the flight stack. Let's watch the video.
Hi, Jesutofunmi. I don't know if
Yeah.
there's a sound in the video because I can't hear any sound from my own end.
Oh, okay. I could actually hear sound from my end, but probably it's not going through the Zoom application. But I'm sure we can all see, right?
Yeah, we can see clearly.
Good, good, good. All right.
Okay. Is the sound necessary or something we can do without?
Now I think we can do without the sound actually.
Okay, good.
So now, the video you just saw was actually a drone system I built from scratch. Though the flight controller is what I built from scratch at this stage. So I made the hardware by myself, everything from scratch, designed the entire thing. I developed a firmware, a custom operating system called Cherubim OS. So it was a basic, they call it cooperative priority-based scheduler. So I built that too as well from scratch, and a simple flight stack on top of that called Angel Flight Control System. So that is what handles the state estimation, sensor fusion, PID control, and whatnot. So now I'm going to explain actually what makes all this possible. So I'm going to take you through the process of actually building this. So what is a flight controller? A flight controller is actually the brain of the system if you are simplifying the entire activities. So it's constantly trying to answer three simple questions. Where am I? what is changing, and what should I do next. So the user, let me say the user flying the drone using a radio control transmitter is trying to tell the drone to pitch forward, pitch backward, or roll right or roll left, I think, or any command. Now, it's the job of the flight controller to take that input, use the data gotten from the sensor, and make some computation and make the entire drone respond properly to that user's command. And all this stuff, all this job is doing it thousands of times per second. Now, let's move forward. What are the components that make up a flight controller? So the blocks I have here is just a simplified format. The flight controller is actually more complicated than this, but this is a simplified form. So basically, the flight controller is made up of sensors. We have the microcontroller unit, a firmware running on that, and a control algorithm running upon that. So all of these things come together to just make a one working system. So let's go deeper. So in our next slide, we want to look into the sensor part. So while I was building the flight controller, it took me years. I'll kind of come that openly. It took me a long time actually working on this flight controller. I actually started, I think, at least 5 years. 5 years ago. It's a very, very long time. I had to build the courage enough to even try to even attempt to even give the flight controller building activity a chance. So what I did was I actually broke the entire thing down. So I'm going to take you through my own process. I actually did it. So what I did was I look at what made up a flight controller, like I've shown you before. Sensors, there's the control side, there's the firmware side, there's the microcontroller side, and there's some other parts like communication, storage, and fail-safe. A lot of things that are actually there on board. But I started with the sensor part because the sensor is a very, very critical part of the flight controller. So the sensor we'll be looking at now is the IMU. The IMU is actually called Inertial Measurement Unit. Its own job is actually to measure the physical orientation of the drone in the air. So for a basic IMU, like what we're looking at now, we have what we call a 6-axis IMU. So there's like 9 axis, like the one on board the flight controller I built is a 9-axis IMU. What makes up a IMU generally is a gyroscope and accelerometer for a 6-axis IMU. But for, let me say, a 9-axis IMU, you will have a compass or a magnetometer being fused together to make a 9-axis IMU. So in this case, I'm going to be just exploring a simple 6-axis IMU configuration. So a 6-axis IMU just combines a gyroscope and an accelerometer. That is what makes up a simple 6-axis IMU. Now, the kind of technology that the IMU that I've selected and we normally use, popular ones in orbit drones, is MEMS. MEMS means micro electromechanical system. So now inside the flight controller, one of the most important things in IMU, like I've said, the way it actually works is very, very, very interesting. Now, these sensors actually have tiny moving structures. So because they are like at silicon level, and they're very, very, very small. So when the drone moves, these tiny structures also move in response. So this movement, this motion that these tiny structures make is being converted into electrical signals, and it is these electrical signals that we read, and we use that to process the state, the orientation that the drone is currently in. So that's what we actually read. So we're not actually guessing the motion, we're actually measuring it physically via these tiny structures. So now to the gyroscope. The gyroscope is actually a sensor that actually measures rotation. It measures how fast the drone is moving in a particular axis. So, like I said, for the 6-axis IMU, we have 3-axis gyroscope, we have a 3-axis accelerometer. So, for the gyroscope, we are measuring angular velocity, or simply called rotation, around a particular axis. So since it's three axes, we are measuring around three axes. So they are simple structures that are actually configured or made, built on a particular axis to sense the rotation on that axis, like your X, your Y, your Z. So once the drone rolls to the right or rolls to the left, the sensors can pick up the angular velocity at which it's rolling or pitching forward or yawing clockwise or anti-clockwise. So the gyroscope is actually a very fast sensor, very fast. It can measure very fast. Like the one I have on the flight controller I built, actually you can sample at 8 kilowatts max frequency, while normal sensors might work at 1 kilowatt, some even less. So it's very fast and very responsive. But it has one problem. It drifts over time. So let me say you have a flight controller in your hand and you are rolling, let me say to the right at 15 degrees per second, or let me say 1 degree per second. It's going to read that for you naturally. But let's say you put the flight controller on the table, on the floor. It has a little drift. It might be reading 0.01 degrees per second, which, if integrated, might accumulate over time. So it has, in some way, it has a little drift problem. So let's go to the accelerometer. The accelerometer actually measures accelerations along each of its axes. So I said the IMU is made up of, the 6-axis IMU is made up of a 3-axis gyroscope and a 3-axis accelerometer. So this accelerometer measures accelerations along each axis. So like the X, the Y, the Z. Now, for the accelerometer, we can actually derive the orientation of the drone at a particular point, let me say at rest. It's very stable. It does not drift, but it has a problem as well. It is very noisy during motion. Let's say you are moving the flight controller of the drone right to the left, they are moving it aggressively. The data you are going to be getting from the accelerometer is going to get inaccurate because the data becomes very noisy during motion. Now, when let's say you've attached the flight controller to the drone and you turn on the motors, let me say independently, the vibration caused by those motors can also impede and affect the accelerometers. So we have two sensors now that one is fast, but it drifts over time. We have another one that is stable, that does not drift, but is noisy in motion. Now, let me show you how we fix this problem. We fix this problem with what we call sensor fusion. Like we take the data from the accelerometer, we fuse that with the data we get from the gyro. Now, a simple algorithm would be a simple filter, or a simple sensor fusion algorithm would be the complementary filter. So just a simple explanation of what it does is that it takes the reading from one sensor, like a gyro, which is not noisy, but it drifts over time, and it fuses that with the accelerometer reading. But we have a coefficient, in which we normally call the alpha coefficient. So that tells us which particular sensor do you trust more. So in application, what we normally do is this. We trust more of the gyro reading because it's not noisy, but it drifts over time. But we use the reading we get from the accelerometer to kind of correct the gyro reading over time. So when the drone is stable and let me say it's not moving aggressively, we take the reading from the accelerometer, we derive the position of the drone in the air using trigonometry, then we use that to actually compensate and correct the gyro data. So that's just simple way of how sensor fusion works. There are more advanced like sensor fusion algorithms like standard Kalman filter, Mahoney, and some other advanced heading resolution systems. So, but in this case, we're just going to look at a simple one. So let's go to the next one, control. Now, we've gotten the state estimate of the drone. We can kind of make out where the drone is in space. But now we still have a user input to respond to. We have to control the system. We have to compare where the user wants the drone to be and where we actually are, right? So now the job of the control is to look at the difference between where we are and where the user wants the drone to be and drive that error to zero. So we kind of correct the difference. That's what it simply does. Takes the input from the user, takes the current state of the drone, look at the difference between them, and drives that error to zero. That's as simple as it gets. That's how simple the control is. So let's move forward. Now, to now show you how critical and serious tuning control of the drone is. It's a very, very serious stuff. So I will give you a story of myself. While I was developing the flight controller, I was tuning the flight controller, the PID parameters like the proportional, the integral, the derivative parameters of the controller. So I at that point in time, I had not figured out the issue that was wrong with my flight controller that was not making it to fly, that was not making it to behave properly. So I was still trying to see if I could tune it out and solve the issues with more tuning or things like that. So there's a way I normally hold the drone. I normally hold the drone like from top, then I kind of hold it down to the ground. Then I observe any behavior in it, and I use that feedback to retune the drone. Now I was tuning a particular parameter, which is the integral parameter. So just a simple controller in this setting, it can be a PID controller or PIDF controller or some other advanced control algorithms. But in my own case, I use the PID controller. So there are three parameters. Like I said, the proportional. The proportional does respond instantly with a particular factor, a particular multiple. The integral kind of corrects error over time. So let me say the flight controller is actually off. The 0 point, let me say the point where the user wants to be, let me say for a long amount of time, let me say 2 seconds, 3 seconds, it begins to integrate that error
Ticket.
over and over and over again. It begins to, can you
Give
hear me?
me 500.
Okay. So it begins to integrate this error over and over again and takes that and multiplies that by the error and gives that to the actuating peripheral, right? So there's the derivative. So that one just kind of reduces how fast the system responds to an error. So that was the basic simplified version of what these parameters do. So I was tuning the integral term at that point in time. So what I didn't know was that there was serious delay in the system, that the control algorithm was using the sensor data that is late because there's a delay in the system, right? It's taking the sensor data and acting on the sensor data that is already late and is not what the actual state of the drone is, not actually telling us the current state of the drone. It's like some milliseconds late. Now, I was just tuning this parameter, and the drone became very unstable, and the propeller ended up cutting my forearm. So they actually bled out to like plaster that around and continue the tuning. So this thing that moment made something very clear, that this thing is not forgiven. Air robotics is not forgiven. Tuning real-time control systems is actually not forgiven. It's not just code, it's physical. Mistakes actually have real consequences. You don't just make an error in code and it just goes scot-free. It might result to actual physical damage or physical injury like I had in my kids. So I just wanted to make that clear. So now let's now go to how we actually build these things. So if you want to build a flight controller from scratch, there are three layers we have to kind of take into consideration. Now, there's the hardware layer, there's the firmware layer, and there's the flight stack or the control layer, or we can also call that the middleware. So let's take this layer one step at a time. So let's look at the hardware layer. The hardware layer is where trust begins. We have, the sensors, we have power, we have layout. Now, let me show you actually my own flight controller board. I don't know if you can see my screen or you can see my camera feed, but I'm actually holding up a flight controller in my hand. So, but I also have the picture of the flight controller actually in the slide, right? So here we have this part. These are the parts where the sensors are. There's the IMU. There's a 6-axis IMU here, complemented with an accelerometer and a full-blown 9-axis IMU. So my own flight controller hardware has two 9-axis IMU. So there's what we call redundancy. So we are like, I have a backup sensor in case something goes wrong with the main sensor. So because the application of to which I targeted the flight controller for is precision agriculture. So, and we need precision, we need reliability in that kind of application. So we have the sensors, we have power, like this big capacitors that show where power section is. We have the microcontroller and some other parts of it. So this part is actually a very, very critical part. It's the foundation of the entire thing, the entire system, the entire flight controller. So because the flight controller is not just the hardware, we have the firmware and we have the middleware. So if you get it wrong on the hardware side, you run into a problem that the software or firmware side cannot solve. You have sensors picking up noise. You have maybe power instability, the microcontroller running into a brownout. So brownout is when the voltage, the input voltage is lower than what is recommended for the microcontroller. So that's a brownout scenario. So to actually build your own, I will take you through the process of building a flight controller. So for the hardware, you start with a system design. So not everybody has to make the flight controller like I made mine, or make it like Pixar will make theirs, or make it like Auterion or APM or any other flight controller vendor. You have to look at where you want to use the flight controller. You might be using yours in a ROV situation like an underwater drone. You might be using yours, let me say, in a let me say like a quadcopter or a fixed wing aircraft or an unmanned ground vehicle or any manner of application. That application should define what you do with your flight controller. So first thing you do, like I said, is to make a system design. Like I said, the system design is influenced by your application. So let us take my own scenario, for example. I wanted to make a flight controller that targeted precision agriculture. Now, I know that precision agriculture requires a lot of sensors because we want to, let me say, spray pesticides or fertilizer over a particular field. We need precision in navigation, precision in sensing, and a lot of things. So that's why I put a lot of sensors on my own and I added redundancy. So for you, you might want to target an FPV, that's a first-person view, a drone that majorly is used in, like, this war in Ukraine versus Russia. So your own might be that where not so much sensors are needed. But let me say your own application is in defense where your system has to be very, very reliable. You might even go an extra step and add more redundancy because it must not fail. You understand now? Now, depending on your application, you get your system design, and depending on that system design, you select the components that make up your flight controller hardware. Now, let me say you are picking a microcontroller, for instance. You have to pick, let me say your scenario requires a lot of sensors. You most likely will want to pick a microcontroller that has a bigger bandwidth, that has, let me say, DMA. DMA means direct memory access, that has good clock frequency. You will not want to use an 8-bit microcontroller. You preferably use a 32-bit microcontroller like I'm using. You might want to use a microcontroller that has a lot of communication peripherals, support for real-time operating system, like the one I'm using support what called SysTick, that's system tick. So there's a lot of features you have to look at that has to match your own system requirements. So that will affect your component selection. Like for me now, I have storage on board, like SD card slot. I have an FRAM on board. I have connectors like for CAN, for USB, for I2C, external ADC port, button, buzzer. All that depends on your system, what you actually want. Also, when you've picked your entire component, you select your components, you've made your schematic, you have to be careful about your layout, the layout, power, how you route the board, where you place some particular sensors. For instance, the sensor, the magnetometer, is a compass which I have on board on this flight controller hardware. It's a sensor that's very, very sensitive to electromagnetic interference. So you don't put that near your power side where your power block is. You don't put that close to the motors. You put it somewhere that is not easily influenced by the electromagnetic field coming from the motors or the electromagnetic field coming from the power section. So you have to be careful of your layout. Also, you have to be careful of power. So you have to know the power budget of your own device, the power budget of the flight controller you are building. So you have to know that the power input you are given, the wattage, the rating can bear the power draw you are going to take from it. You understand that now? So let's move forward. We've spent a lot of time on hardware. So let's move forward to the next stage, which is firmware. Now, firmware majorly handles timing. In my own case, it was I had to make a custom operating system called Cherubim OS. So I started, some people might ask, why didn't you use FreeRTOS or just use bare metal? I first started with bare metal. I made progress. I went to FreeRTOS because I had multiple tasks I wanted to run simultaneously. But because of my application and the control I wanted, and I wanted more control on timing, I ended up having to build my own operating system from scratch just because I wanted control. Because timing is everything. In a real-time system, you don't want to make mistake on your timing. Just like I told you about the injury I had on my forearm, right forearm, it was because of a lag in the system. I I did not take note of the time at that point in time, and I got myself injured. So if your system reacts too late, your drone reacts late, and that leads to instability. And instability can cause the entire drone to be damaged, can cause you personal injury or injure another personnel. So that is something you have to take full control. So firmware controls timing, and you have to take timing very, very seriously. So in this firmware layer, you also have what's called hardware abstraction. So now, because this is like a simple three-layer system, we have the hardware, we have the firmware, we have the middleware. We also do what we call hardware abstraction. We don't want the middleware to have direct access to the hardware. All we want the middleware to worry about is data. So we don't want it knowing what the exact registers that is controlling the IMU, the exact registers of the GPS, the exact registers of the GPIO, the exact registers of the communication peripheral. We don't want the middleware knowing that. So the firmware also handles hardware abstraction. It does not allow the middleware, the flight stack, to know exactly what the hardware is exactly doing. So, and this also helps with made it's possible for you to port your flight stack to another hardware. That is why you can see autopilots can be used on, let me say, PX4 running using SM32 or ES32 or running on a Linux powered board. That is why that's what the firmware does. It abstracts that. So because the flight stack is abstracted from the actual hardware, it can run in a different scenario, in a different place, on a different platform. It can even be simulated on your hardware, on your own host system, like a laptop or something like that. So let's go to the middleware. Now, the middleware actually runs the control. It handles control. It handles the sensor fusion algorithm. It handles like navigation guidance and navigation, things of that sort. Now, this part is where, like I said, is normally abstracted from the hardware, abstracted from the hardware, and it takes control from the user. That's because it runs the control algorithm part, the control logic. It takes input from the user, in any form, in any communication form. Like in my own time, for my own hardware, I was using XBus, that's serial bus, from the RC receiver, takes that in without having to know exactly the peripheral that's handling that communication, without having to know what exactly that one is doing. All you just get is the data from the receiver, from the user, via a remote radio control receiver, then works on that, gets data from the sensor, as a logic block, get data from the sensor, computes that, do sensor fusion, runs its own PID loop, and moves forward to controlling the motors. It actuates the motors. Now, to buttress my point, I want to explain to you what happens if you don't actually own that autopilot stack now. So there was a particular time I was working on a bespoke remotely operated vehicle, an underwater vehicle. So for the MVP, we were using Pixel running ADTC, and we're using a Raspberry Pi 4B running BlueOS. Now, according to the design, it was expected to work to do what the MVP wanted to do. But the actuators on that particular ROV, it was an underwater ROV, was very different from what the common setup, the common ROV on the market would be. Because it's a very bespoke actuating peripheral, I cannot really say. But it was so different that the Idle Pilot and the Idle Sub and BlueOS combo could not actually meet our requirements. So much so we had to build a workaround. I had to develop custom intermediary modules that actually take the actuating signals from the BlueOS and Idle Sub combo and actually convert that into what that actuating peripheral will understand. So even in fact, we had to actually let me say quantize and kind of to be able to downplay some things. We had to reduce some things like the communication between the actuator and the system was meant to be duplex. So duplex will mean that I can talk to the hardware and the hardware can talk to me at the same time. But because of the software architecture, the design of the BlueOS and Arduino sub combo, the fly stack, we had to reduce it to a simplex communication. So that means the autopilot can only talk to the peripheral and the peripheral cannot respond. So that made us that's why I now recommended that we have to make our own fly stack from scratch. So this is an instance where building from scratch actually makes sense. Now I'll give another story. So earlier when I was developing my flight controller, it was still very, very, very early in development. A company reached out to me about their flight controller vendor that actually changed policy. So the flight controller vendor, I think, changed their policy on them and it affected them negatively, right? So, and they could not move forward. So because of that, the company reached out to me saying if I could support them, if I could maybe support them with a flight controller. But at that point in time, it was still very early. I couldn't support them. So they were stuck. But they had to find their own way out. So either they had to work with the bad policy or they had to find another person else. So that's the risk of dependency. So if you don't own the stack, you don't actually have full control of the product's future, of the entire product. So your roadmap will depend on someone else. I'm sure we'll get that. So when does it make sense to actually build from scratch? Honestly, it's not every time you have to build from scratch. It's not always. If your goal is to actually build a minimum viable product or quickly get your product to the market as soon as possible, it is best and very advisable that use existing systems, what actually exists on the market, like your Autopilot or Betaflight, CleanFlight, anyone that works for you. It's better use that to quickly get to the market because in business, time is money. That speed, that time to market guarantees your position in the market. So, but if your system is not standard, like the case scenario I had with the underwater ROV, if your case is not standard, you might really want to consider building from scratch. If you have custom requirements, your system is performance critical. It has, let me say, you're in defense, you're working in defense, and you need that reliability. And the stacks on online, the stacks in the market might not give you that reliability you want. You might want to build them from scratch. Or you need full control. You don't want to depend on someone. You don't want to have licensing issues, like this story I told you of, where the vendor changed policy. You don't want to run into that kind of issue. Then building your own becomes very, very, very necessary. Now, who is it for? Is it for everybody? Actually, it's not for everybody. Not everybody can just say, I want to build a flight controller from scratch. It's not for everybody. But if the goal is speed, you can use what exists, like I said earlier. But if your goal is control, ownership, and long-term advantage, then this is the path. Now, I'll give you a business view of what this actually does. Now, let's go to the next slide and I show you the business view. Now, what does owning the stack gives you? Building from scratch, having the entire stack, what does it give you? You actually gain control. You gain flexibility, you gain leverage. Now, you will not be limited by someone else's system. Let me give you an instance, right? If you own, like now in my experience of building flight controller from scratch, I'm not actually limited to selling the drone, let me say the entire drone as a product. I can also sell the flight controller. Now, the critical intellectual property I gain that I gain in building from scratch can be applied in a lot of other places. Like now, the same IMU component that you find in the flight controller is also in the gimbal. Like your hand and gimbal, you find it there. In your smartwatch, you find it there. Like in the smartwatch, the IMU is used as a pedometer. You guys have to count your steps and know your orientation. Also, it's used in gesture control. Like let me say in your VR, your XR stack, it's also there as well. It's in your laptop, like in some Dell laptops. If the laptop drops, let me say while the system is operating, it can stop the HDD, the hard drive working, and keep prevent the hard drive from crashing. You can also find that in your cars as well for crash detection. You can find that in avionics. You can find that on ground vehicles. Even in your phone, you can use that for knowing the difference between landscape mode and portrait mode. That same intellectual property. You have freedom to innovate. Also, let me say you have different applications for the same product, right? You can, rather than, let me say, giving an example here, right? We have, you can apply flight controller into precision agriculture. You can also use that in hobbyist applications. Like, let me say you want to just fly for fun, you want to use it in toys. Some of the requirements that might be needed, some of the components that might be needed in a precision agricultural application might not be needed for a toy. You understand? So the same intellectual property still goes into developing the flight controller for agricultural, precision agricultural purposes, and you can also use that same intellectual property for a toy drone purpose, saving you costs. You can reduce your component, you can reduce the component for the on the toy application, and use the required components to meet your system requirements in the precision agriculture component. So precision agriculture application. So now you can actually get more margin. Like for the fact that just raw materials come into your industry, your company, and the full product comes out, you don't have to depend on any other vendor. Let me say the person making the flight controller hardware or giving you the software changes policy or runs out of stock. You don't have to depend on on another product vendor. All you just have to do is let me get some components from bigger vendors like let me say SM Microelectronics, like ST Microelectronics, then ESP, or any other component you need. All you need will be raw materials coming in and the final products coming out. So, like I said, just to recap, once you own the stack, you gain control, you gain flexibility to innovate, and you have leverage. You can do a lot of things, a myriad of things once you own the stack. And also, you won't be limited by someone else's system, someone else's hardware assumptions, someone else's software architecture, someone else's priorities. You'll be free to do what you exactly want to do. So, own the stack or be limited. So this is what I'll leave you with. If you don't control the fly stack, you don't control your product. Now, building from scratch is not about doing the hard things, doing things the hard way. It's about owning the most important part of the system. It's just the difference between using the technology and actually building it. Thank you. If you have any questions, let me know. Thank you.
Oh man, this was amazing. I have a lot of questions, but let's let's make other people ask. So questions. So if you have a question, you can unmute. If you feel comfortable talking, we would actually prefer you unmute your mic and talk. But if you feel that might be challenging for you, you can actually use the chat section.
Hi, I have a question. Hello, can you hear me?
Yeah, Lemo, we can hear you.
Oh, okay, okay. Just want to be sure. Um, my question is actually about because what caught my attention was the Blue OS that when you were trying to interface it with the flight controller, because I faced similar problems, especially when using Blue OS, and I had to like revert and change some things as well. So, I just want to ask, were you able to solve the issues with the communication, or you just abandoned it and like moved to building your own?
Okay, let me answer the question. So, the application actually worked in the way it's
Hi,
supposed to work.
Tifumi. Did
So,
you get Lemo's
okay,
question? Okay.
yes, I got that. Yeah.
Okay.
Okay, so the application actually worked the way it was supposed to, according to its own capacity. We do not really have much issue between the flight controller and the Raspberry Pi 4 running Blue OS. I think when I was doing this, there are some Raspberry Pi supported by Blue OS, so that you have to use. So we just flash the entire Blue OS on the SD card, load that up in the Raspberry Pi 4, put that in Raspberry Pi 4. Then we used USB. We connected the PICSock. I think we used this cheap early PICSock that we used, connected that with the Raspberry Pi with via USB, and we just did some configuration and we got it to work. But the main issue was that the system we're working on, had a custom peripheral, actuating peripheral. Most RV on the market, they use thrusters, but for some actuators, we're not using thrusters. Some part of it were not thrusters. It was a custom peripheral. So it was different from what normal RV, normal actuators that RV on the market use. So that's where we had the issue. We did not really have the issue with Blue OS and ADOSOP among themselves. We did not have that issue from outside. It was fine for me. I hope that answered your question.
Okay, yeah. So how did you, based on the interface, like right now? Let me just even tell you a problem that I'm facing. I'm just trying to come up with a different way of figuring it out. Where the right now I'm using ROS 2, right? ROS 2, and the I'm trying to use the Blue OS, flash the Blue OS on the Pixel, the flight controller. But the normal stack is expecting the thrusters, thruster command. But the problem is that I'm not using thruster command for navigation. I'm using uh, uh, things for navigation. What would you advise I do there?
Oh, I remember. Okay. I understand. I get this point. I think I faced that issue and I solved it actually. So what I had to do was I had to recompile Hadoop Pilot on its own. So there's a particular
Okay.
there are points in the Hadoop Pilot code where you can make custom actuator like mappings, and you have to
Yeah.
recompile and make your own custom firmware, your custom firmware and bootloader for the Hadoop Pilot. So Hadoop sub. So we actually made a custom image where I had to, download the entire Hadoop Pilot stock, the Hadoop sub, download the entire code base. I had to recompile this, set up the tool chain, make the map, and configure it and flash it onto the hardware. So you really have to go and do that actually. Truly, yeah, you have to do that.
Okay. Yeah. Thank you.
Wow.
Yeah, that was
I have a question.
okay, sure. Mojaji, you can shoot. Mogaji,
Mogaji.
sorry. Yeah, Mogaji.
Wow, like this is very information packed, and I'm super glad to be on the call. To start with, I would love to ask questions around autonomous vehicles, yeah. So imagine we are trying to do like a military grade uh drones. What do you think would be your advice with regards to the field, the issues you think we're going to face, and the things we should be looking out for? That's one. So with regards to autonomous flights, do you currently have like a full level personal build that you think we should discuss with, check on? It's something you've built that is completely custom, that anyone we are discussing with or you're discussing we can pick up from and use to build whatsoever they are currently working on.
Okay. Firstly, if you are building for, let me say, defense, that's a very, very interesting field to build for because they are very, very keen on reliability. You don't want to mess up with defense. So, because let me say, in what scenario you want to protect a particular asset, there's no chance for mistake. So, normally, if I'm to let me say target or do something for that kind of scenario, I normally go down to first principles and make a system design. You understand? Like now, I'll give you a simple example. There was a particular time when I was to work on a particular, most times I work on bespoke things, so I cannot really say as much. But there's particular gear I was to develop for a particular person, a particular company that was used in weapons for not Nigerian anyway. But because of the application, because like the one that's used for defense, the components I had to select changed just because it was going to be defense. Because now uh, we don't want latency. Like we don't want there to be lag or delay in response. We don't want that, right? So back to what I'm talking about. If you're going to develop anything for defense, you just have to just go down to system design, look at what are the requirements, what are the things you cannot take, what are the things that are very key to you that you can actually forfeit. So, like, let me say, more popular things that happen is communication. That's one thing in defense. Like that's why most drones in the Ukraine, Russia use fiber optic fiber optics cables for transmitting. Jamming, that's there. Also, flying without GPS is a very popular thing now that most companies are coming out to do. So you have to consider that as well in defense. So you have to find a way to get one over your opposition. You understand? Make sure they can't jam you, their signals. They can't, yeah, maybe using kinetic ways to shoot you down, like shoot the drone down.
Yes,
So a
yes.
lot of things
This
you have
is a
to.
middle one.
There's a lot of things you have to. Yeah, so a lot of things you have to take control. Sometimes you can use stochastic behaviors. So stochastic just means noisy, like something that's unpredictable, like Brownian motion. So let me say you want your drone to behave in a Brownian motion so that it's not easy, it's not an easy target. That's just one idea. There's a lot of things you can consider in drone in defense applications, but you just have to know where the drone to use it for. There are some that are for reconnaissance, some that are for actual fights that they want to actually take someone out. Some are just there just to just gather data. So your application matter even in defense. Defense is still a big space. So you have to know where are you targeting? Where are you looking at? What area of this defense section are you targeting? So that's that one. So I think you talked about custom autonomous stacks. So at this point, I'm actually the product is still developing. I have the mind to make it ready for people to just come and access and use via some contract and agreement. But I've not yet developed it to the point where I can give orders for testing yet. It's almost like it's also me and the system now at this point. So what I'm currently doing is I'm working on making it something that I can package well enough that other people can also test and use without me having to explain a lot of it to them. You understand? So at this stage now, yeah, I've had some people that want to, want me to help and they want to use some of my stuff, but I would say honestly, it's not yet fully mature to, to be used by other people yet. But I will appreciate if people want to come and see what I'm doing and see how I can help them. I hope that answers your question.
Okay, that's very, very interesting. With regards to the last thing you said, I would love to talk about it after now, so we could see what you're already doing and how we can be part of it. We actually are already doing something in the idea of swarm drones that are autonomous, majorly currently around just information gathering. So we came up with a
Okay.
thing where if there were drones already in like the real time information. So for us, right, it's in real time information. But we also know that there's a whole lot of things around being autonomous. The one that you mentioned without the GPS thingy. Like that's also something that we're heavily looking at. So I don't want to take over the call and unnecessarily just keep rambling. So we'll probably do more talk, please. Thank you so very much. I learned a whole lot from this.
Thank you. Thank you.
Right. It's a wonderful conversation going on here at the ADTC Frontier session live. And just to inform everyone who is currently not on the ADTC Discord community, do well to join the community. The link to the community we posted on the chat session, and the conversation after you get the available. So do well to join the Discord channel. The link will be shared shortly on the chat session. Please, there's still more time for questions if any part is not clear. For my own question, Jesutofunmi, please confirm if you can hear me.
Yeah, I can hear you.
Okay, so recently, due to the heavy use of drones in warfare, as we've seen, the tide of war is changing. Can you throw more light into how the communication, drone communication has migrated from conventional cell towers like GSM, GNSS communication to leveraging fiber optics? Can you explain kind of in details that solves the problem? And is this the telcos infrastructure or the communication infrastructure we have here in Africa, precisely Nigeria?
Okay. Okay. So now it's all started with normally for a simple communication system between, let me say, the controller, the user, let me say, using a radio control transmitter and the drone itself. Generally, we use what we call RF, radio frequency, very popular, right? So there are some advanced way of modulating signals on top of that, different ways. But those signal frequencies, like popular ones, use 2.4 gigahertz. That's a very popular band. It's called ISM band, Industrial, Scientific, and Medical band. So because they know the frequencies, so normal people in a war scenario, everybody can, the opposition can blast a very, very loud, I'll call it loud, but it's not actually loud in sound, but loud signals that can disrupt slight, small signals that, going between the drone and the controller, the radio transmitter. So now, to kind of combat that, the particularly in this Ukraine war, they switched to fiber optics, where the drone is physically tethered to the controller, to the remote control, the radio control, via a fiber optic cable. So the data is just being sent via light, pulses of light to the drone, and the drone responds. So whatever you do and you jam and you try to jam, nothing's going to happen, because the medium at which the data is flowing through is no more the air, it's no more using a radio frequency, it's now via light in a fiber optic cable. Now, as regards the GNSS and GPS, also GPS is also using radio frequency. So now, we have satellites in the air that in the space that can come together and triangulate via some little computation. We can triangulate your location using multiple data from different satellites, using the delay in timing to kind of get where you are in space on the Earth. But like I said, there are also radio frequencies, so they can also be jammed. So they can just blast high noise signals, high noise in that particular frequency band, and you won't be able to get any GPS triangulation, any GPS location. So what they now do is, I think one of the common method to combat that, even though it's still coming up, is visual odometry. So you are using cameras to kind of know where you are. So like we have this popular ones normally flow sensor, like visual flows, optical flow sensor. So you can find them in let say commercial drones that can be made to fly indoors. So rather than relying on GPS, they use optical flow, like changing pixels to kind of know okay, I've been here before. Just like your mouse. Your mouse is kind of your optical mouse uses visual odometry. So if you move the mouse right up and down, there's no ball, like no like olden day mouse that use ball. You're just using camera, like using pixels to kind of count and check where am I in space, how many steps have I moved forward, Similar, it's a simple thing, similar thing to optical flow. So to counter GPS jamming, they kind of try to use optical flow. Though in the defense scenario, it is not yet fully in operation. Like from what I can tell, it's still manual. Like humans have to, fly using FPV goggles and using their own brain to know where they are and go to their target. So that kind of a thing. But it's still coming up. Visual GPS and visual odometry is still coming up more and more.
Okay, so we've migrated from using radio frequencies, which is RF, to using light. So currently, there's no technology that can disrupt the communication sent via light rails. That's my question one. And also, in terms of, I mean, I've used some drones where I plan the flight. So, for instance, I wanted to go to coordinate A, carry out a mission, maybe to take an image, coordinate B, drop an item, then return back to base. You get so in that case, I don't really need. I've already planned the flight path. I don't need to communicate to it. So, would there be any need for me to build a drone that requires um, um, not using RF because I'm not communicating with it. It already have the information it needs to execute a successful flight, and so I'm not concerned about anybody jamming it. So I think those are my two questions. I don't know if you can throw some light to that.
Okay. Firstly, for fiber optic communication, there's no actual way to jam it. It's just either you cut the cable itself. So there's no actually, from as far as I know, there's no way to jam the fiber optic cable because you are not in the same medium. The medium of communication is in the fiberglass itself, the thin piece of glass. So it's because we're in the same medium of air, that's why we can jam RF frequencies trying to pass through the air. That's why we can jam that. But since we are in different mediums, just like something in the water, because you are not in the same medium as water, whatever is going through the water, you cannot really jam externally without being in that medium. You understand? So the way to kind of, that's just my little explanation about that. The way to disrupt signals or actually disrupt that medium itself, like cutting the fiber optic cable. Two, as regards waypoint. So in defense, we have like key requirements that you have to meet. So you don't want your drone flying on its own with no communication to you. Communication is key in defense. That is why you really want communication with your device, with your drone in the air. So let me say for you, like you said, you sent waypoint. Don't forget that waypoint is dependent on GPS and GPS also using RF. So if they jam that RF of that GPS, your drone is down all the same. So no matter what you do, you still have to find a way to escape and find a work about that particular constraint. Like I said again, defense has a lot of tight constraints. Like let me say, let's take for example a missile, right? A missile is not using GPS. It uses like some of them use its tracking. They just lock onto some of them use GPS, but that might not be exactly what they might be depending upon. They have redundant peripherals to kind of, in case that was not working, they can still get to their target. Some of them might use visual, they use thermal, you understand, to still track their target. So like I said again, defense has tight constraints. So you really want communication. You have to find the workaround to still get communication between you and your device. Thank you.
All right. Thank you so much. That was awesome. Any more questions? If you don't feel like turning on your mic to ask a question, you can actually drop it in the chat section. And also remember that the conversation will still continue, you know, in our Discord channel. So endeavor to join the channel. The link to join our Discord community is on the chat section. So click on the link if you're not on the Discord community. Okay, it was building UAV flight controller from scratch, owning the core of your products. It's very important, and Tufumi has given us a whole lot of insight. And so, I mean, how many of us are actually in the space of? I mean, we have about 20 something persons on the call right now. Just to know who is actually in this domain, be it from the business sector or the technical sector, you can just indicate by raising up your hand or reacting. Who are, if you're building UAV, AUVs, if you're writing firmwares for smart systems, you're a CAD designer, you actually develop virtual reality systems that communicate with drone, you can just indicate. That's the essence of this community for us to know what people are doing and how we can create this cross collaboration among different sectors and achieve first principles here in Africa. So while we wait for people to indicate and react to that, so this is for Tufumi. So being someone who has played in the UAV space for quite some time, I think going to 5 or 6 years. So can you share your insight into what space actually have that high use case for drone UAV technology in Nigeria, in Africa, from your own point of view? And why do you think that is the space, be it agriculture, defense, and considering the recent funding in hard in deep tech coming into Africa, especially in um, in the hardware drone space. So what do you think? What's your view for people on this call right now, or people who will listen to this session later on? What do you think is your point of view in the markets and the ecosystem?
Okay. For me, Nigeria is a quite interesting field. I would say if Africa itself is a quite interesting field. So, my own aim when I came in for, let me say, building fire controllers from scratch was I was aiming for agriculture. There's something that actually could, benefit us as a country, benefit us as a continent, something that can actually make us more productive. So the use case me actually have a lot of interest in is agriculture, right? Because when I started, I look at how expensive DJI drones are, particularly the agricultural drones like DJI. I think there's a Agras M1, there's T40, T20, T30, big agricultural drones, very, very, very expensive, that are being, made from China and sent to us. And sometimes the terrain we have might be different from the terrain they have, right? So looking at, why is there nobody building for our own terrain, building for us exactly, that actually knows our problem and can solve our problem, right? That's why I kind of ended up going into precision agriculture and trying to build up something from that. So when I started, actually, I was looking at the price, that they were very expensive. How could I make it cheaper? But after some years in this stuff, I know that it's not easy to make it cheap. So you might have to just you might have to just spend the money. So for us, I think the best use case would be what makes us productive. If it's let me say videography, if that's what makes us more productive, that can help us develop as a country, help us bring more increase buffer the economy and help the economy, that's be fine. let me say, inspection, building, let me say like 3D mapping. That also is a very, very good use case for us in Nigeria and in Africa. So defense too is actually a good case too, as it helps it helps buttress our own power to buffer our power. And look at now Ukraine, looking at Russia-Ukraine war. Normally, from just looking at the numbers, you will say Russia has way more power than Ukraine. But just that shift in dynamic that Ukraine had in making drones and use that in the war, help them turn the tables for them and is making them better in the war, I've given them a bit more edge in the war. So for us, I would prefer use case that helps our economy, gives us more power, and actually help us to solve more problems that look at us that can also be extrapolated to other countries. Like if you take other people that make products from other countries, they mainly started solving their own problem, right? So then other people seeing that, oh, you solved your problem for yourself. Please, can you solve mine for me? That kind of a thing. So if we start solving our own problem, then we can be called to solve other people's problem, and that also helps us in the long run. Thank you.
Okay, that was brilliant. Agriculture, um, we need more of this precision farming and to boost our yield. So we have just one person who indicated is actually playing in this domain. That's Lemuel. Yeah, and quite specific in the AUV, autonomous underwater vehicle research work he's currently doing at Sheffield Hallam University. And it's good to have more people who are developing such research projects in this part of the world. And so one of the reasons or one of the missions of ADTC is to see how we can de-risk people doing deep tech. And yes, you've mentioned a lot of challenges we faced, and platforms like this give us the opportunity to bring people together and then give them what they need, the required resources from manpower, because it's something that is quite overlooked in this part of the world, but it's very important, and down to the financial resources and the support to build from first principles. You get, because a lot of people have these ideas, a lot of people are eager to build and solve this problem, but they just need to overcome that the ability to start. The ability to start is very important, and that's why we have sessions like this. And we have more programs coming up in the ADTC platform, and so keep for you to be updated and keep up the track with our engagement from our hackathons to other activities we have. Endeavor to join the Discord community, and you're going to get more of this. So before we wrap up the session, maybe we can have some final statements from Tufumi. And don't forget that the slide and other resources will be available on Discord community immediately after this session, and also the recording too will be available on our YouTube channel, so you can actually get it and watch too, for those who joined late or those who really want to have a rewatch to gain more insight. So Tufumi, over to you.
Okay. What I'll say is I'm really looking for people that can actually build, like I'm saying, from scratch, that will actually be like DJI, be like Apple, be like Tesla, be like SpaceX. I can actually do things by themselves from scratch and own the technology. I don't want us as Africans, always depending on other people, depending on other vendors, depending on other countries. Like now, we have all these political superpowers, like countries like China, USA, they have, most of them, like Russia, they have some things they've done by themselves that make them unique. But we can't say as much for us. We buy things from other countries, from other manufacturers. I really wish and I desire that we as Nigerians, as Africans, can actually come together and take up the challenge to actually go down to first principles and build this thing from scratch. And in the process, I can assure you to a particular degree that in the process of making the attempt to build from scratch, you learn some things and you find that you are not constrained to one form of application. You find out that there's another problem that that same technology can solve. There's another solution that will be more optimal if you use this technology. So I'm just imploring that we all strive to be the next SpaceX, the next Tesla, the next Apple, the next DJI, and the next Microsoft. Thank you all.
Okay, that was something worthy of note from Jesutofunmi. And thank you everyone for joining this session. And we are expecting you all to stay active on the Discord community as more updates will be coming up from the special channel we'll be creating to continue the conversation on our community. And do well to follow us on all our social media platforms, from LinkedIn to Twitter, Instagram, everywhere you can find us. And also subscribe to, you can follow us on Substack too, and stay updated with every activities we're doing here at ADTC community. And yeah, so any final questions before we call it a wrap? If there's none, thank you everyone for taking our time to join the session. And our next live session will be coming up next month. And also, you can stay tuned for our research review activities that would likely kick off from hopefully next week, as we are trying our possible best to see how we can actively ramp up on that. And like you heard from Jesutofunmi, yes, we're looking for people who can build from scratch, who actually do things from first principle point of view. Yes, very important. And the community is here to support you. The community is here to give you a voice and backing that you need to really, really push things forward. Yeah. So once again, thank you everyone for joining this session. You made it amazing one, and see you all in the community and next month for our next live session. Bye.
Bye. Thank you. And thank